Somewhere, out past the orbit of Jupiter, a chunk of ice and rock that may have formed before our sun even existed just swept through our solar system. It came from nowhere near here. It is not going to loop back. And when NASA pointed the most powerful space telescope ever built directly at it, the readings that came back left scientists genuinely stunned. If you have never heard of an interstellar object before, stick around, because by the end of this video, you will understand exactly why astronomers around the world dropped what they were doing to study this thing, and why what Webb found inside its gas cloud is being called one of the most important discoveries in modern comet science. And if this kind of real, source-backed space content is what you come here for, go ahead and hit that follow button now, because we are just getting started. Let's set the stage first with something simple. Our solar system is basically a gravity trap. The sun sits at the center, and everything close enough gets pulled into an orbit around it. Planets, moons, asteroids, comets, all of it. Some of these objects take a few months to circle the sun, some take hundreds of years, but they all have one thing in common. They are bound. They go round and around forever, locked in by the sun's gravity, never truly leaving. But every so often, something enters our solar system that does not play by those rules. It does not belong here. It is not looping around anything. It came from somewhere else in the galaxy entirely, and it is only passing through once, on its way to somewhere else, never to return. Astronomers call these rare visitors interstellar objects, and in all of human history, we have only ever confirmed 3 of them. The first was spotted in 2017. It was small, strangely elongated, almost cigar-shaped, and it tumbled through space in a way nobody had ever documented before. It showed almost no visible activity, no obvious tail, no glowing cloud of gas around it, which made it incredibly hard for telescopes to study in any real depth. By the time astronomers fully grasped what they were looking at, it was already too faint and too far away to learn much more. To this day, parts of its behavior remain debated simply because there was never enough time to gather the data needed to settle the argument. The second interstellar visitor showed up 2 years later in 2019. This one behaved much more like a familiar comet, with a visible tail and a glowing coma, the cloud of gas and dust that forms around a comet as it heats up. Because it was more active, scientists were able to pull a richer set of chemical data from it than they ever managed with the first object. Still, by the time telescopes were tracking it closely, it too was already heading back out of our solar system, and the observation window closed faster than anyone wanted. Both of those encounters left the astronomical community wanting more. They wanted a third interstellar object, ideally bigger, brighter, and more active, discovered early enough that the world's best instruments, including newer tools that did not even exist back in 2017, could get a real detailed look before it slipped away again. That moment came in the summer of 2025. On July 1st, 2025, a telescope network called ATLAS, short for the Asteroid Terrestrial Impact Last Alert System, caught a faint, fast-moving point of light during a routine nightly sky scan from a station in Chile. ATLAS exists mainly to catch potentially dangerous asteroids early enough to calculate whether they might threaten Earth, so most of what it flags is completely ordinary. This one was not ordinary. Astronomers quickly ran the numbers on its trajectory, and within days, they had their answer. This object was moving far too fast to be captured by the sun's gravity. It was not going to settle into orbit. It came in, and it was going to leave again, permanently. This was officially the third confirmed interstellar object in recorded history. It was given the name 3I/Atlas, with the 3 marking its place in that short, exclusive list, and Atlas honoring the survey system that first caught it. From the very first calculations, something about this object stood out. Its path around the sun was more sharply bent, more extreme than either of the 2 interstellar visitors before it. Here's a simple way to think about that. The shape of an orbit tells you how tightly something is bound to the sun. A path that curves gently and loops back around belongs to our solar system. A path that comes in fast, barely bends, and shoots straight back out belongs to something just passing through. 3I/Atlas had the most extreme, most sharply hyperbolic path ever measured for an interstellar object, and it was moving at a genuinely staggering speed, well over 200,000 kilometers per hour when it was first detected, picking up even more speed as it fell toward the sun. Now here is where the story gets genuinely wild, and it is the reason NASA's own researchers and outside scientists were so eager to study this comet in detail. Based on how fast it is moving relative to the average motion of stars in our region of the galaxy, researchers were able to put together a rough estimate of how long this object has been drifting through interstellar space since it was first ejected from whatever star system originally built it. That estimate landed somewhere in a wide range, roughly 3 to 11 billion years old. It is important to say clearly that this is not a precise, locked-in number. It comes from modeling assumptions about galactic motion, and the uncertainty is large, but even the low end of that range puts this object in the same neighborhood as our own solar system's age, which is about 4.5 billion years. The high end would make it older than the sun itself, That means it is genuinely possible, not confirmed, but genuinely possible, that this comet formed around a star that lived and died long before our own sun ever ignited, and it has been drifting alone through the emptiness of the galaxy ever since, untouched, until it happened to cross paths with us. Sit with that for a second. A frozen fragment of a solar system that might not exist anymore, possibly older than the ground you're standing on, close enough for our telescopes to actually study. What made this encounter even more valuable is that, unlike the first interstellar visitor, which looked mostly quiet and inactive, 3I/Atlas turned out to be a genuinely active comet. As it approached the sun and warmed up, frozen material locked inside it began turning directly into gas, streaming off the object and forming a glowing coma, along with a faint tail. That activity mattered enormously to scientists, because an active object releases its internal chemistry out into space where telescopes can actually detect and analyze it. A silent, frozen rock keeps its secrets. An outgassing comet hands them over. It is also worth pausing to appreciate how much coordinated effort goes into catching something like this at all. Survey systems like ATLAS scan enormous portions of the night sky over and over again, every clear night, comparing new images against old ones, hunting for anything that moves. The overwhelming majority of what they catch is ordinary asteroids safely orbiting within our own solar system. Catching a genuine interstellar object is a massive bonus, like finding a single specific needle inside an almost unimaginable haystack of nightly sky images. And because ATLAS caught this one early, astronomers around the world got something they never really had with the first two interstellar visitors: real lead time. Months of advance warning before the comet's closest approach to the sun, which meant space agencies could actually schedule time on some of the most in-demand telescopes on the planet, instead of scrambling at the last second the way teams had to back in 2017 and 2019. Once the hyperbolic orbit was confirmed and the interstellar origin was locked in, observatories across the globe, along with space telescopes orbiting far above Earth's atmosphere, began lining up to take their turn. Now let's talk about the star of this story, the James Webb Space Telescope, often just called JWST, or Webb. Webb is the most powerful space telescope humanity has ever built, and it does not see light the way our eyes do. Instead of visible light, it is tuned to infrared, a type of light with longer wavelengths that lets it pick up heat signatures and chemical fingerprints completely invisible to normal telescopes. That makes it perfect for reading the precise chemical makeup of a faint, distant object like a comet. Here is something interesting, though. Webb was never really designed with fast-moving small solar system objects in mind. Tracking something moving as quickly as 3I/Atlas across the sky pushed the telescope's tracking systems in ways engineers had not fully planned for. Despite that challenge, the team managed to lock Webb onto the comet in August of 2025, capturing its first detailed spectrum, essentially a chemical fingerprint written in light. Then, after the comet swung past the sun and started heading back out of the solar system, Webb observed it again in mid-December of 2025, this time using its mid-infrared instrument, capturing the most detailed chemical readout ever taken of an interstellar object. What came back surprised a lot of people, including the scientists who had been waiting months for this data. For one, Webb found that the coma surrounding 3I/Atlas held an unusually large amount of carbon dioxide compared to water vapor, a ratio far outside what astronomers typically see in comets that formed here in our own solar system. Comets we have studied for decades tend to follow fairly predictable patterns in how much water versus carbon dioxide they release as they warm up. This visitor broke that pattern in a big way, hinting that whatever environment originally built this comet was chemically different from the one that built the comets native to our own solar neighborhood. Then came the discovery that really made headlines. Buried in that mid-infrared data, researchers identified a clear signature of methane gas streaming off the comet. This marked the first time methane had ever been directly detected coming from an interstellar object, something that had never shown up on either of the two previous visitors. Alongside the methane and carbon dioxide, Webb also confirmed water vapor being released, and then something genuinely unexpected on top of all that, a very specific atomic signature belonging to nickel. Finding a metal like nickel escaping from a comet's coma is unusual, and it tells scientists something about the raw ingredients that were mixed into this object when it first formed, likely billions of years ago, around a star system that has nothing to do with our own. So why does the methane detection matter so much? Methane is a small, lightweight, fairly fragile molecule. When something is exposed to raw cosmic radiation for long stretches of time, exactly the kind of radiation an object drifting alone through interstellar space for potentially billions of years would be constantly hit with nothing at all to shield it, that fragile methane tends to break down or boil away from the outer surface. Because of that, researchers did not necessarily expect to find much methane left near the surface of an object this old. Finding a strong, unmistakable signal of it was a real surprise, and it forced the team to think carefully about where exactly it was coming from. The leading explanation researchers have put forward is that the comet's outer layers lost most of their original methane over the billions of years it spent exposed to deep space radiation. What Webb was likely picking up instead was methane escaping from deeper material underneath the surface, material that had been shielded from that radiation the entire time, only now being exposed as the outer layers boiled away in the heat of our sun. In other words, Webb was not just reading the surface of this ancient visitor. It was reading straight into material that had been sealed away and untouched since long before our own solar system existed, only now seeing daylight, or in this case, sunlight for the first time. That is a genuinely remarkable thing to sit with. A team of scientists pointed a telescope at a fast-moving speck of light, and that telescope managed to read out the actual chemical ingredients of a piece of another solar system, ingredients that had been frozen and hidden for possibly billions of years until this exact moment. Webb was not working alone on this either. NASA's Hubble Space Telescope also studied 3I/Atlas, both shortly after its discovery and again after it swung past the sun. Hubble's early images gave researchers a rough first estimate of the size of the comet's solid core, the nucleus, buried underneath all that glowing gas and dust. Later observations, once the comet's activity had settled down after its closest approach to the sun, allowed for cleaner measurement, separating the faint glow of the solid nucleus from the much brighter surrounding coma. Here is something worth being honest about. The nucleus size estimates for this comet have shifted more than once as new data came in, and there's still genuine scientific debate about exactly how large the solid core actually is. Some analyses point toward a nucleus a few kilometers across, noticeably larger than either of the two interstellar objects discovered before it, while other researchers have argued the true mass and size could be even greater than early estimates suggested. Rather than treat this as a settled number, it is more accurate to say that 3I/Atlas appears to have a larger, more massive nucleus than its two predecessors, and pinning down the exact figure is still active work. That larger size is part of why this comet became so much brighter and easier to study than the two before it. A bigger nucleus means more surface area available to heat up and release gas as it nears the sun, which means a brighter, richer coma, and ultimately a stronger, clearer chemical signal for instruments like Webb to lock onto. Size alone does not guarantee good data, but in this case, it gave scientists a real advantage compared to the fainter, smaller objects seen in 2017 and 2019. Measuring a comet's solid nucleus is trickier than it sounds, by the way. From a telescope's point of view, the tiny solid core is almost always drowned out by the much brighter cloud of gas and dust surrounding it. Astronomers have to combine brightness measurements at different wavelengths with assumptions about how reflective different surface materials tend to be, in order to separate the faint signal of the actual icy core from everything glowing around it. That is exactly why nucleus estimates for this object kept shifting, starting with a wide early range and narrowing, though not fully settling, as more observations rolled in. Webb and Hubble were not the only instruments involved either. A sky survey space telescope called SphereX, designed to scan the entire sky in infrared light, took its own look at the comet in December of 2025 and picked up signs of increasing activity after its closest pass by the sun, along with dust made of tougher, more heat-resistant material mixed into the coma, plus additional gas signatures that added even more detail to the chemical picture. Ground-based radio telescopes using a technique called ALMA also joined in, detecting other molecules escaping from the comet, including methanol and hydrogen cyanide, adding still more pieces to the puzzle of what this ancient visitor is actually made of. Now, because this object was moving on such an extreme path, and because it turned out to be surprisingly large and potentially very old, some corners of the internet ran wild with speculation, floating theories that it might not be a natural object at all. And look, when something unusual shows up from outside our solar system, it is a completely normal human instinct to wonder what else it could be. Scientists took that curiosity seriously rather than dismissing it outright. Researchers pointed radio telescope arrays specifically built to search for what are called technosignatures, meaning any kind of artificial radio signal. That might suggest an object was built rather than formed naturally, directly at 3I/Atlas during its passage through our solar system, and listened across a wide range of frequencies. The result was clear. No artificial signals were detected. Every piece of data collected, from Webb's chemical fingerprint to Hubble's imaging to the radio searches, points to exactly what you would expect from an ancient natural comet. Its behavior lines up with known cometary physics. Its chemistry, while unusual, fits within the broader range scientists expect from an icy body that formed around a different star. Its coma, its gas emissions, its dust, all of it points to a natural interstellar comet, not anything constructed. That is worth saying plainly, not to shut down curiosity, because honestly, the verified science here is already remarkable enough without adding anything to it. A confirmed visitor from another solar system, possibly billions of years old, carrying chemical fingerprints that may have been frozen since before our own sun existed. studied directly by the most advanced space telescopes humans have ever built. That does not need embellishment. The real story is stranger and more grounded than the rumors floating around online. So, what does all of this actually mean going forward? And why should it matter to someone who is not an astronomer? For one, every interstellar object we get the chance to study up close hands, scientists a genuine physical sample of material that forms somewhere else entirely, around a star system we will almost certainly never visit or directly observe in detail any other way. Instead of only theorizing about what other star systems might be made of based on distant starlight, an interstellar object lets researchers directly measure the raw ingredients that built planets and comets somewhere else in the galaxy. That is an extraordinarily rare opportunity. We have only had 3 chances like this in all of recorded history, and 3I/Atlas gave scientists by far the richest data set of the 3, largely because of its size, its activity, and the sheer amount of advanced instrumentation available to study it compared to what existed back in 2017. There is a bigger picture forming here, too. Each interstellar object we detect adds to our understanding of how common these wandering visitors actually are throughout the galaxy. For a long time, scientists genuinely debated whether objects like this were rare, one-off events, or whether space is actually full of them, quietly drifting past undetected simply because we lacked the tools or the timing to catch them. The fact that we have now confirmed 3 of these objects in under a decade, with detection technology improving every year, suggests these visitors might be far more common than anyone originally assumed. As newer, more powerful sky survey telescopes come online in the coming years, scientists expect the detection rate of interstellar objects to climb significantly. In other words, 3I/Atlas may not turn out to be some rare, once-in-a-lifetime event. It might just be the 3rd confirmed sighting in what becomes a fairly regular stream of ancient visitors quietly passing through our neighborhood, most of which we simply have not had the tools to catch until now. That thought alone should change how you look up at the night sky. Somewhere out there right now, more fragments of other solar systems are likely drifting through our own, ancient, frozen, and completely unnoticed, waiting for the next telescope powerful enough and lucky enough to catch sight of them before they slip back into the dark. There's also a very practical reason astronomers are pushing hard to build better detection systems. A newer ground-based survey telescope, purpose-built to scan the entire visible sky every few nights with extraordinary sensitivity, recently began full operations. And many researchers expect it to dramatically speed up how quickly future interstellar objects get identified after entering our solar system. More warning time means more opportunities to line up instruments like Webb and Hubble well in advance, the same way astronomers managed with 3I/Atlas instead of racing against the clock the way teams had to with the very first interstellar visitor back in 2017. Every improvement in detection technology directly translates into richer, more detailed science the next time one of these ancient wanderers shows up. It is also worth remembering how much combined international effort went into understanding this one comet as fully as possible. The initial detection came from a ground-based survey network. Confirmation and orbit calculations involved observatories and researchers across multiple continents comparing notes within days of the discovery. Space telescopes operated by different agencies took turns studying it from orbit, each one contributing a different piece of the chemical puzzle. Radio telescope arrays added even more detail from an entirely different part of the light spectrum. This is genuinely one of the more impressive examples of global scientific cooperation happening quietly in the background. Teams around the world sharing data and coordinating schedules, all working toward one shared goal, understanding a single ancient visitor as completely as possible before it disappeared from view for good. Let's take a moment to really sit with the full timeline here, because it helps put the scale of this discovery into perspective. This object may have formed billions of years ago around a star that might not even exist anymore, in a completely different region of the galaxy. At some point in its ancient history, gravitational interactions with other objects, or perhaps a close encounter with a passing star, likely flung it out of that system entirely, sending it drifting alone through the emptiness of interstellar space with no star to orbit, no light to warm it, just endless cold and silence. For possibly billions of years, it drifted like that, tumbling through the space between stars, completely untouched, carrying its original chemistry sealed away and frozen. Then, purely by chance, its long silent journey happened to bring it close enough to our sun that our solar system's gravity could finally bend its path, and our telescopes could finally catch sight of it. It swept past the sun, warmed up just enough to release some of that ancient frozen material into space, giving our instruments a brief window to study it, and then it continued on its way, heading back out into the depths of the galaxy, most likely never to return. Think about that against the full span of human history. Telescopes themselves have only existed for around 400 years. Space telescopes capable of reading the precise chemical fingerprints of a comet have only existed for a few decades. Out of the billions of years this object may have spent drifting silently through the galaxy, it happened to pass close to our sun during the exact narrow window of human history when we had both the knowledge to recognize it as interstellar and the technology to study it in real time. A few hundred years earlier, and it would have simply been an unexplained, blurry point of light in the sky if anyone noticed it at all. We happened to be alive, with the right telescopes pointed at the right patch of sky, during the one brief moment this ancient traveler passed close enough to notice. That is an extraordinary stroke of cosmic timing, and it took an enormous amount of coordinated effort and engineering across multiple observatories around the world to make the most of that narrow window, before the comet faded from view for good. Scientists are still working through the data collected from 3i/Atlas, and more detailed findings are expected to keep emerging over the coming months as researchers dig deeper into everything Webb, Hubble, and the other instruments managed to capture. Early findings have already been shared through the scientific community, helping confirm its ancient, cold origins and cementing its place as the most thoroughly studied interstellar object humanity has encountered so far. Every new detail adds another piece to a much bigger puzzle about how solar systems form, how common interstellar wanderers really are, and what other star systems out there in the galaxy might actually be built from. To wrap this up simply, in the summer of 2025, a fast-moving object was spotted crossing through our solar system, and within days, scientists confirmed it did not come from anywhere near here. It was the third confirmed interstellar object in recorded history, and it turned out to be one of the most extreme ones ever measured, moving on the sharpest, most hyperbolic path scientists had ever tracked. Rough estimates place this ancient comet somewhere between 3 and 11 billion years old, meaning it is genuinely possible, though far from certain, that it formed before our own sun even existed. As it swept past the sun in the fall of 2025, it heated up and became active, releasing gas and dust that our most advanced telescopes were finally able to study directly. The James Webb Space Telescope captured detailed chemical readings showing an unusually high amount of carbon dioxide, the first ever direct detection of methane from an interstellar object, clear water vapor signatures, and a rare atomic signal from nickel, all pointing toward chemistry that likely formed in a completely different star system from our own. Hubble helped narrow down its size. Other instruments like Sphere-X and ground-based radio telescopes added even more chemical detail, and dedicated searches for artificial signals came back completely clear, reinforcing that this is exactly what it appears to be. A genuine, natural, ancient piece of another solar system passing quietly through our own before heading back out into deep space, most likely never to return. That is the real story, backed by real data from real telescopes, gathered by real scientists working together across the globe to make sense of one extraordinary visitor. If this gave you a new appreciation for what verified space science can actually uncover, follow this channel, because we are going to keep tracking every confirmed development on this story and every other major discovery like it as new data continues coming in. Drop a comment telling me which part of this surprised you the most, and share this with someone who would find it as fascinating as you clearly do. We will see you in the next one.